Okay, hello MEGN 416 students. Welcome back to another exciting video lecture. So today, or not today, this particular lecture, for this video, what I want to go over is I want to go over quiz 6, which we took right before the shutdown. Overall, about half the class got the right answer and did a great job, but some of the class is still getting the wrong answer when they're coming to getting their equations in motion. There's a couple students who are struggling, and then a few students who just kind of made a couple little organization or typo mistakes that were really associated with actually setting up the position equations. So this is the type of problem that would show up on the exam we're having. So I want to make sure we go over it again and we go through that whole process together. Let me see if I can find, I've got my notes. Oh, pardon me, I just burped. I should edit that out, but knowing me, I probably won't. But remember, there was a video lecture that I posted online on Canvas about the 14 steps that we do. So please make sure, if you aren't getting 100% of your quizzes, please make sure you go through that and review it, and make sure you own those steps, because those steps are going to really help make it so you make fewer mistakes and get these equations in motion correct. Because if the equation motions are incorrect, then you really didn't do anything. You did stuff, but if it doesn't work, then you didn't do it. Just like if you paid some plumber to come out and fix your toilet, and they did a bunch of stuff, but your toilet still doesn't work, did they really fix your toilet? No. So we have to set up the equations in motion correctly, just like you expect a plumber to fix your toilet. Okay, anyway, so here we have this problem. And for step 1, I think I remember, let's put that to preset so the custom colors are the same. Step 1, one of the first things I do when I look at a problem like this is I look, okay, what are the displacements, whether they're rotational or translational. In this system, what we have is we have a rotational, and this is the degree of freedom that they're interested in, okay? And let's make that a little bigger, okay? And then I'm going to go from left to right. So I'll call this displacement x1, this displacement x2, and then project that up, and this displacement x3, okay? And I know what you're thinking, Dr. Hildreth, x1 and x2 both the same. Why are you doing that twice? Really is going to help me keep things clear, okay? And I'm going to call this K1 and this K2, okay? And then this bar has uniform mass M, okay? So under my givens, I might also put K1 is equal to 3K and K2 is equal to K. That way it's there when I need it later. Next we got to do is we got to take these things that we've drawn out and figure out how they're related to our degree of freedom, our displacements. So we know that we're going to call theta equal to theta and theta dot equal to theta dot. Okay, and I know what you're thinking, why do we do this? We do it because we are being explicit to ourselves and anybody else who might follow our work later of what is the degree of freedom that we're choosing, right? So here, theta is our degree of freedom. We're telling them explicitly theta equals theta. That's the thing that's our degree of freedom. Okay. Next, we've got x1 is equal to something. So let's figure that out, because a handful of students got that wrong, and we don't want to make that type of mistake, because we don't want to be making trig mistakes at our level if we can avoid it. Okay, so this distance is still L over 4, and from SOHCAHTOA, okay, I've got my angle. I'm interested in the opposite. That means I'm interested in the SO part. So sine theta is equal to x1 over L over 4. Okay? And that tells us that x1 is L over 4 sine theta. Okay? A handful of students had this backwards and put 4 over L sine theta, which isn't the type of mistake we want to be making. Okay? And then x dot 1 is equal to, well, I'm going to come down here and figure that out. So x dot 1 is equal to dx1 dt, which is equal to d of L over 4 sine theta d theta times d theta dt. Because remember, we got to apply the chain rule, because the thing we're interested in, the thing that's varying with time, which is theta, is embedded in another function. So that gives us L over 4 cosine theta, theta dot. Okay, so L over 4 cosine theta, theta dot. Okay. And then x2 is equal to L over 4 sine theta, x2 dot is equal to L over 4 cosine theta, theta dot. Okay. And then x3 is going to be equal to 3L over 4, because you've got this L over 4 and this other L over 2. We're going to add them together, times sine theta, and x dot 3 is equal to 3L over 4 cosine theta, theta dot. Okay, so let's talk about organization real quick. There was a kind of a common theme I saw for the quizzes, for this quiz, where the students who had these steps, I wonder if I can make something that these steps kind of really well organized, tended to get all the right answers. Whereas the students where like this was over here and this might be somewhere over here, it didn't go as well, okay? And that's usually a sign not that you don't understand the material, but you aren't confident in your approach. So please make sure that you're taking the time and following an approach where it's consistent, where you're doing the same operation over and over again in the same location, and that you're getting all your mise en place together. I mean, maybe I should go and figure out if I can get a Top Chef subscription for the whole class, and everybody would know what I mean by mise en place, but try and get everything together. Okay. So the next step that I've added recently, because I thought it was, when I was talking with the student office hours, because I thought it was a really good step, was to see, okay, why don't we make sure we're accounting for all the things with kinetic potential and energy loss, damping, okay? So the first thing, let's list our T's, our kinetic energies. What's going to give us kinetic energy? Well, we're going to have kinetic energy from this bar right here, okay? So that's the kinetic energy of that mass, okay? And I think that's the only kinetic energy we have because the springs are massless springs, okay? Now, something to think about for a problem like this, for an exam, is how could I make this problem more complicated? Like, could I go and put a mass for these springs? I probably could. Sounds like something I'd do. So be sure you practice that. Okay, so anyway, there's a kinetic energy. Now let's look at the things that are going to store energy. We're going to have this spring storing energy, this spring storing energy. And I told you in class that you could ignore this mass that's going to deflect, I guess, upwards a little bit. Because that's the center mass for it. But I'm going to solve the problem on the assumption that maybe I didn't say that in the exam, or maybe you didn't hear me, just to show you that it ends up going away. So I'll put the potential energy of the center of gravity of that bar, and then we're going to have K1 and K2, okay? And then I'm going to save myself a little space and keep it a little bit cleaner. I'll make this mark, okay? And then one of the things I'm going to have R is going to be this damping right here, okay? So I would normally not be making all of these circles on my work, and it's making me die inside, so I'm going to get rid of those. Okay, so this is a good step for the mise en place, is listening to yourself, what are the things that have kinetic potential and damping energies. That way, when you're going and making them, there aren't any that you're going to miss. Because a couple students missed, or one student I think missed this R, and then I think that was the only one I saw, but I think it's a good technique. So now we'll see what the potential energy is. So, okay, and let's go back to black. Okay, so the kinetic energy of that mass is equal to 1/2 J of the mass theta dot squared, okay? And I gave you what J was for this particular system. So now we could put that in, 1/2 times 7/48 ml squared theta dot squared. Okay, good. Now, I'm going to move that down just a little bit and over so I get that room back because I'm going to be using it. Now, let's take a look at the potential energy of that mass, okay? That's going to be mg times delta H, okay? And in this case, delta H is equal to x2. So it becomes mg times L over 4 sine theta, okay? So once again, this column right here is for the energy in whatever coordinate system makes sense for that energy, okay? And then this column right here is when we're translating that system into our degree of freedom that we're interested in, okay? And then there's that one. Let's now look at the potential energy of K1. Okay, that's going to be 1/2 times 3K, because K1 is 3K, and let's check our work. Yep, okay, that's good. 3K times x1 squared. So it's 1/2 times 3K times L over 4 sine squared theta. Oh, there, Nelly. Got a little ahead of myself. Sine theta squared, which is equal to 1/2 times 3KL squared over 16 sine squared theta, okay? And then UK2, which is equal to 1/2 times K times x3 squared, okay, let's make sure, yep, okay, x3 squared, which is equal to 1/2 times 3K times 3L over 4 sine theta squared, which is equal to 1/2 times, oh, whoa there, Nelly. There is no 3 there. Look at that. Translation, you know, just get used to talking, not thinking, and you make mistakes, or at least I do. So 9KL squared over 16 sine squared theta, okay? Now, that looks really tedious, right? That's what we want. We want tedious stuff because when it's tedious and you're doing the same thing over and over again, you can go back and check. Is that K? Is that K? Is that K? Did I get that squared? Did I get that? Yep, that squared. Did I remember to square the L squared? Yep, okay. So you can go back and check your work. Checking your work is an important skill that has to be practiced and developed. Because as much as people seem to tell students that somebody's going to check their work, nobody's actually going to check your work for a lot of industries. So let's look at the energy lost in this damper. That's 1/2 C x2 dot squared. So that's 1/2 C, and x2 dot would be L over 4 cosine theta dot squared, and that becomes 1/2 C L squared over 16 cosine squared theta dot squared. Make that a little neater. Okay. So at this point, I've done all the hard work. At this point, assuming I did it right, we're good. So let's go back and let's check our work, because I rarely show in the videos me checking my work. So let's check my work. Okay. Theta dot. X1, L4 sine theta. Yep, that's L for 4, and that's a sine theta. Cosine theta dot, L4, yep. X2 is L over 4 sine theta, cosine theta, yep. And then 3 is that 3/4, yep. Sine theta, okay, we're good. So I made those marks so you can see me checking my work, and in an exam situation or something else, you will see me check my work repeatedly, okay? So let's check this work, okay? 1/2 J theta dot, that's the correct equation. 7/48 ml squared, yep, that's correct. Ooh, whoa there, Nelly. And theta dot, okay. MGH, is it M? Yes, it is M. G got there, and then H is X2. X2 is L over 4 sine theta, yep. Okay, XK1, 3K, is that 3K? Yes. X1 is L over 4 sine theta. L over 4 sine theta, correct. And did I square everything? Yep, squared. Okay, that's got all the squares. Okay, x2 is k, or yep, that's k, and x3 is the distance. Okay, 3l over 4 sine theta, 3l over 4 sine theta squared. 3 squared would be 9, l squared for 16 is my sine squared. C x dot 2, l over, nope, this would be the cosine version because it's x2 dot. C x2 dot cosine squared 16. Okay, we're all good. So normally, like I wouldn't have this, I would tap this lightly with a pencil. It wouldn't make a mark, but I wanted you to see how I go through it. And it's really, please practice this. It's good engineering practice, and it's going to help you out for quite a while over your life, at least with regards to vibrations and equations of motion. Okay, so now we can do dt d theta dot, and this becomes 7/48 ml squared theta dot. And those are zeros because they aren't t's. And dt d theta dot ddt, so this becomes 7/48 ml squared theta dot double dot. Okay. And dt d theta, which is 0, and all the rest of those are not t's. And then du d theta, that's not a u, okay. And then dum d theta equals d of mgl over 4 sine theta d theta, which becomes mgl over 4 cosine theta, which now I can apply the small angle theorem. That becomes 1. This is mgl over 4, which equals a constant, which means I get to ignore. Okay, so I'm just going to put that to 0 right now. And we should ignore it. Right, for this point in time, we ignore constants. That would have actually been taken care of when the system was originally set up. Okay, now du k1 d theta is equal to 1/2 3kl squared over 16 times d sine squared theta d sine times d sine d theta, and that becomes 1/2 3kl squared over 16 times 2 sine theta times cosine theta. Now apply small angle theorem. That becomes 1. That becomes theta. Those cancel out, so we end up with 3kl squared over 16 theta. Okay, so 3kl squared over 16 theta. Okay, and here's a good time to stop. Check your work. Right, if I have a system that's rotating, these distances L, they better be squared. And yep, I've got it squared. And okay, is my 3 a 3? Is that a 3? Okay, I remember to include the right spring constant. Okay. Okay, and then the du2 is pretty much the same. I can just take this number right here. So that becomes 9kl squared over 16 theta. Okay, and then this one right here, drc d theta dot is equal to, well, that's the theta dot right there. So it becomes 1/2 cl squared over 16 cosine squared theta times d theta dot squared d theta dot. Okay, so that just becomes 1/2 times 2, pull that out, cl squared over 16 cosine squared theta, theta dot. Okay, those cancel, that goes to 1. So this becomes cl squared over 16 theta dot. Okay. Okay, there we're good. There we're good. That was tedious, but not hard, okay? So now I'm running out of page, so I'll go to the next page. So now I can write my equations of motion. J theta double dot. Well, actually, that's not J at this point. Rookie mistake. This is 7/48 ml squared theta double dot plus cl squared over 16 theta dot plus 3kl squared over 16 plus 9kl squared over 16 theta is now equal to 0. So MEQ is equal to 7/48 ML squared, which is equal to 7/48 times 100. And L, I think, was 4 meters squared, which should be 233 kilogram meters squared, okay? Now, I'm not going to check your units on the exams or anything, but it is a really good habit to get your units correct, because when you're practicing your units, you actually end up having a better understanding of the relationships between things, believe it or not. So CEQ, that was CL squared over 16, which is equal to 100 times 4 squared over 16, which is equal to 100 kilograms seconds meter squared. Okay, I think I got those units right. And then KEQ. KEQ is now 3KL squared over 4. Oh yeah, so if you add these together, I didn't show my work, I apologize. That becomes 12/16 KL squared, which goes to 3/4 KL squared. Okay. Just so you've got that work there. Apologize for not showing my work. So it's 3 times 100 times 4 squared over 4, which is equal to 1200 Newton meters. Okay, so let's check a couple things. Was everything 100s? Okay, everything, I did plug in the right numbers. I did plug in 4. Okay, that would be a good time for me to go and check my work. And then I would also, of course, check my numbers at this point, okay? So we are almost done with this happy problem. Okay, so omega n is equal to the square root of KEQ over MEQ. Let's write that a little bit neater. KEQ over MEQ, which is equal to the square root of 1200 over 233. Okay, which is 2.27 radians per second. Okay. And then zeta is equal to C over 2 square root of MK. And there are a lot of versions of rearranging M and K. There's omega n something. I just do this one because I find it easier. You can use the one that makes you happiest. 233, that's 1200, equals 0.095. And that one doesn't have any units. Actually, that wasn't an answer. There we go. And then omega d equals omega n, the square root of 1 minus zeta squared, which is equal to 2.27, the square root of 1 minus 0.095 squared, which is equal to 2.26 radians per second, is equal to omega d. Okay. So there we go. That's that problem solved. Please be systematic. This will be a good time to go back and check your work, because we all make mistakes, but engineers are paid to not be able to just do the work, but to go back and find their mistakes and correct them before they turn in their work. Just like if you had a plumber, you'd want them to check their work, make sure nothing's leaking before they leave your house. Okay, thank you everybody, and I will see you online shortly.